Thank you for the nice introduction, and thank you for the invitation. It's a wonderful place.
Is the last speaker?
Yep, I think so. I switched the box on. Is it clear? Yeah, good. Yeah, okay. I will speak loud. So you see that here we have only black clouds, no beach. This is our research building. I actually, when I came into this field, I met Alan Heeger in 1994. So I kind of realized that when I came here, it was like a 20th anniversary. And so that's quite a long time ago. And since then, we worked on the physics of organic devices. So I will talk a little bit about that today. And because it's, of course, a talk for the energy center, I will focus also a little bit on the solar cells. So an outline, I will tell you a bit about general things about charge transport in organic semiconductors, and then some general things about photocurrents. And then the last part, I will focus a bit more specifically on the organic solar cells. Is it too light? Yeah. Oh, okay. Ooh. This is a great risk that everybody falls asleep, but I'll do my best. So one of the first results we had, so about 2 years after we started at Philips on this subject, and we also met Alan, was that we studied to work on MDMO PPV and MEH PPV that was invented here by Fred Woodall in Santa Barbara. And this was the device that we made, so it was not an LED, but we called it back then a hole-only device because you cannot inject electrons. And the nice thing was when you then plotted your IV curves on a log-log plot, you get a straight line with slope 2, which means that the current depends quadratically on the voltage. And in the literature, there is a well-known formula, the so-called space-charge limited current. And what is nice about it, it has the mobility in the prefactor. So, yeah. Yeah, so from the IV measurement, you can directly determine the charge carrier mobility, which was for this polymer something like 10⁻⁶ to 10⁻⁷. So what happens? Why is that? It's because when you start, it's an undoped polymer. When you then add contacts and you apply a voltage, you inject charges in the polymer. And the amount of charges is proportional to the voltage that you apply. It works basically like a capacitor. And of course, the electric field, and therefore the velocity, is also dependent on the voltage. And that's why you get a quadratic dependence. So what is important to realize is that when you have an undoped semiconductor, that when you then apply a voltage, that you change both the charge carrier density as well as the velocity. That gives you a quadratic dependence. So, for example, in Ohm's law that you know from metals, then this carrier density is a constant number. That's why it's then linear. So this is basically something like Ohm's law, but then for insulators. What is different for organic semiconductors compared to silicon and other ones is that this mobility depends very strongly on the charge carrier density. Here you see measurements that we did on LEDs and on transistors. And if you calculate in both devices what kind of density you induce, and you measure the mobility, you get basically a very nice curve that represents how the transport depends on the density. What is, for example, important here, that you cannot speak about the mobility of a polymer, because it depends at which carrier density you measure it. And for example, for this PPV, and when you measure it in an OLED, it's about 3 orders of magnitude lower than when you measure it in an FET. So that's something to take into account. The physics behind it is a model that was developed by Heinz Bessler in Germany. So you basically have a Gaussian density of states because you have a very disordered system. And what happens is if you put a few charge carriers in, that they relax to the tail states, and they end up at a certain level, which is called the equilibrium level. And then in order to transport, they will move up to a higher level, because when the density of states is bigger, that means that the distance between the molecules with that energy is smaller. so the transport is easy. But on the other hand, it also costs you an energy step. So there is a kind of optimum between distance and energy where the molecules go to, and that the electrons go to, and that's called the transport level. Now, what happens now is also that this level is temperature dependent, and also, of course, it depends on the density. And what basically happens in a transistor is this: when you apply a gate bias, you start to increase the density, and that means that the Fermi level starts to rise. And at some point, the Fermi level is above this equilibrium level, and this is then kind of the new starting point to the transport level. And now what you see is that the energy step becomes smaller and smaller when this level keeps on going up. And that's what you see in the measurement. So at this cross point here, between this regime and this regime, so about here, then these two levels are on top. When the mobility increases, then you are in this regime, in the transistor, because you're just making the energy step smaller. So based on these measurements, we made a model how the mobility depends on density and temperature and electric field. And with that, you can very nicely describe the whole current in basically all conjugated polymers. Now, we of course also looked on electrons. Now you make a test device like this. You send electrons in and you do not inject holes, so this is an electron-only device. And now if you look in this plot, this is the hole current, and this is the electron current. So what you see, that in this PPV, MDMO PPV, that the electron current is a few orders of magnitude lower than the hole current, but also that the IV curve is much steeper. So this is a slope 2, that's quadratic. This is about a slope 6. So there is somehow a relation between the current and the voltage of V to the power 6. And then you can look in a textbook, and what you find is that you get this kind of steep IV curves when you have traps in the band gap. And the steepness is determined on how the traps are distributed in energy in the band gap. Later on, I see I'm now at about 2011, we made a model where we have a Gaussian density of states for the free electrons in the LUMO, and a Gaussian density of states for trap levels in the band gap of the polymer. And these are some numbers. The traps are in the 10 to the 17th regime per cubic centimeter. And for PPV, they are typically something like 0.6 to 0.7 EV below the LUMO. So that's nice. But what is kind of interesting, as I said, this is kind of a slope 6. Now you can do the same for other polymers. So you take a whole range of polymers and you make electron-only devices, and you get this steep IV curve, and you look at the slope. And then you find a kind of distribution of numbers ranging from 2 to about 7. But what is interesting is if you plot them versus the position of the LUMO, then you see that when the LUMO is higher, the slope gets steeper, and the LUMO comes down and reaches something like 3.8, and then the slope is suddenly 2. And that's the normal space-charge limited current without traps. So from all these polymers, we made electron-only devices, we measured their temperature dependence, and we modeled them. And what came out was quite surprising to us, namely that in all these polymers, we could use the same amount of traps and in the same position. So it looks like that there is some kind of impurity present in all these conjugated polymers that is the same. So it has an energy position of something like 3.6 EV below the vacuum and a density in the 10 to the 17th regime. So in principle, when we get a polymer and we know the LUMO position, then we know how deep the trap is, and we can almost predict you what the electron current will be, which is kind of strange. So the question is, of course, what are these impurities? And the answer is we don't really know. Jean-Luc Breda and his co-workers, they did some calculations for us, and we looked they looked at different processes like carbonyl groups and the addition of water to the chains, but all of these give a relatively small distortion of the energy levels. There are some complexes, they are called hydrated oxygen. They were introduced by Peter Ho in 2009. They give, in the calculation, very deep energy levels. And so that could be the trap, but we are not sure. I'm only saying here that these kind of impurities would give the right energy level, but that's of course not a proof. It's only a kind of indirect clue, so to speak. So this is something we still have to figure out. So now about solar cells, what you do, you take a semiconductor, you shine light on it, and you get a current. And how does that work? So what is very nice, the basic principles are explained by Goodman and Rose in a paper out of 1971, for which I would, everybody who works on solar cells, I would advise to read this paper first before you read anything else. Now when you read the paper, there are two things that are important, and those are the mean carrier drift lengths, or if you want something like the mean free path. And what you see, the mobility times the electric field, that's the velocity. And when you multiply that with the lifetime of the carrier, you get a distance. So it basically tells something about how big is the distance that the charge carrier can travel before it disappears. And disappears, that can mean that it recombines, or that it falls in a trap, or even leaves the sample. So what happens when you go to very low electric fields, low voltages, then this mean free path for both electrons and holes is small, and it's smaller than the sample thickness. And what happens then is that you generate some carriers, they slowly move, and the current that you derive is basically an ohmic current, where here you see the electric field, and as I said, multiplied with the mobility gives the velocity, then multiplied with the time gives the distance, and G is the generation rate that you can read for that also the light intensity if you want. So this is basically what you do is you just make carriers, and there is an equilibrium between carriers that recombine and carriers that go out of the device. Now, suppose you go to higher voltages in such a way that for one of the two carriers, for example in this cartoon, the electrons have a higher mobility than the holes, that the mean free path of the electrons is bigger than the sample thickness, and for the holes it's still smaller. Now what happens is that the device will help the slow holes to get out. So what happens is the electric field at this contact is increased, and here the electric field is decreased to slow down the fast electrons. So what is important, what happens is that the electric field in the solar cell is not homogeneous anymore. And that has implications for the photocurrent, and what Goodman and Rose calculated was that you get a photocurrent that scales with the square root of the voltage. So that's, you would get something like that. Now if you then go to very high fields that both the electron and holes are extracted without recombination, and then you have the ideal cell, then you basically get a constant current. And maybe you say that's a bit strange, that you get a photocurrent that does not depend on voltage, but it's really not strange at all, because what happens is that the amount of charge carriers that come out of the solar cell is the same as the amount of photons coming into the solar cell. So what happens if you increase the voltage, you extract the carriers a bit faster, but you have to wait for the next photon to come in, and the rate that comes out per second is just equal to the rate of photons, which is a constant. So this is basically what you can find. And then there was one specific case, in the case that you have a semiconductor that has a very low mobility. Then you, for example, in this case, the hole mobility, then you pile up so many holes that you get an electrostatic problem, because charges, they build up an electric field, but the integral over the field, that's the voltage, that can never be higher than the voltage over the sample. And this is called the space charge limited photocurrent. And also for that, Goodman and Rose derived an equation. It's again a square root, but what is different with the other one is that this one is linear in the light intensity, and this one has a power 3/4 in the light intensity. But this was never observed. This was in their paper, but never observed. So now, of course, we look at Bullock heterojunction solar cells, and I'm sure you have seen this picture many times before, because the concept was developed here right in this university. And so you have an exciton, it dissociates, you create free carriers, and you have transport. And one of the questions that puzzled the field for a long time, and still does, is that when an electron and a hole are close together in this donor-acceptor heterojunction, there is still a strong binding energy. And how do you get free carriers? But I will not go into that too much today. So what we did, we said, let's do it in the most simple way possible. We consider that this bulk heterojunction is one semiconductor with the conduction band, or the LUMO, that's the one of the PCBM, and the HOMO is the one of the polymer. Nothing else special. We have two contacts, and that's it. And then you see the experiment. You have the dark current, the photocurrent. You can also look at the difference between the two. You can call that the net photocurrent if you want. And the only thing that we did two things different. We said, well, we're going to replot these data in a way that we choose this point as the origin here. And then we plot the current like that. So we flipped the picture about 180 degrees. And the reason why we do that is that in this way, this is now the electric field in the solar cell. The other thing that we did different, and you can look on the scale, that means here 10 volts, that means that we put something like minus 11 volt on the solar cell. So we went to much higher voltages than what you normally do. But we just wanted to see what happens. Now what you indeed see, there is a kind of linear regime, then a kind of tendency to saturate, but then here there is another bump, which then is not really in agreement with what you would expect. You don't here see any square root or something like that. Now, what is important here is when you now go to these high voltages, like 10 volts in reverse bias, you see that all the experimental photocurrents are on top of each other and they reach a constant. And that's this again, what it means here is that the photocurrent is equal to the amount of absorbed photons. So from this level, you can read how many photons you have absorbed in your solar cell. The fact that, so the current is basically this expression. It's a very simple one. And what we believed was that this decrease of the current here is because this G, this generation wheel, is electric field dependent. Because you have to break up the electron-hole pair, and that you need an electric field for that. And that process is here described by the blue lines. And for example, what you can see here, because you know the maximum number, you can also look at short circuit. That's this point. For this solar cell, the VOC was 0.8. And that means that here is the short circuit point for V is 0. And then you can see that about 60% of the electron-hole pairs was already dissociating. But to get the other 40% out, you had to apply minus 10 volt. And you can read that directly from the graph. So we implemented this dissociation process in a numerical device simulator, and then indeed you could very nicely describe for different temperatures and voltages the whole photocurrent from zero electric field, so this is the VOC, all the way until something like 10 volt in reverse bias. So that was nice. Then we had the question, what happens now when the electron and the hole mobility are not the same in such a bulk heterojunction solar cell. And so what we did, we looked for examples. We took another PPV derivative where we looked for a bigger difference between the electron and the hole mobility. What you see in this device, at room temperature, the electron and the hole mobility are different by a factor of 100. When you cool down a bit to 200 Kelvin, it's even a factor of 1,000 difference. And now when you measure the photocurrent of such a cell, you see already at room temperature, you see a line with slope half appearing, and at low temperature it's very clearly visible. Okay? And now the question was, of course, is this now the space charge limited photocurrent that was described by Goodman and Rose? So for that we had to look at the light intensity dependence. So we looked in this area where you have the square root, and we looked in this area where you have this EGL. So here it should be linear in light intensity, and here it should be 3/4. That's indeed almost exactly what you find. So here there is an almost linear dependence between current and light, and in this region is exactly 3/4. Another thing that Goodman and Rose predicted was that the transition from this regime to this regime shifts with the square root as a square root with the light intensity as well, and also that did it exactly. So this was the first experimental observation of a solar cell in which one of the two charge carriers doesn't want to move very fast, and you can see what the consequence is for the current. And just for you to know, if you have a photocurrent that has a square root, you can easily calculate the fill factor. It's 0.40. So for every solar cell that you make with 0.40, you have a problem. It's a square root. Now, later on, we also looked on more modern polymers in that time. So this was a polymer from Konarka. Was also made also here in Alan's group. There was a lot of work done on this with additives and things like that. But back then, the problem was that the system worked quite nicely. That was before the additives, by the way. But the fill factor was low. So they sent us some polymer over to take a look. And we thought, of course, this is something like 40%, so probably the holes do not move in this polymer. So we did some investigations, but indeed, what we could see was a square root in the photocurrent at room temperature. But what was a bit strange was that at low temperature it was disappearing, and instead of getting longer, like we saw before. When we looked on the transport, so we studied the hole transport and the electron transport, we got numbers that differed like by a factor of 2 or 3. So there was not even a real unbalance. So this would never be a space charge limited photocurrent, because first, the mobilities were too large, and secondly, the difference was way too small. So what happens then, and you can see that in this plot, is that you get a very nice square root, and then the transition to the saturation, but the voltage is also not changing. And this is exactly what Goodman and Rose described for when you have one of the carriers that can leave the cell and the other cannot. In this case, this is called the mu tau, the recombination limited photocurrent. So to summarize it, if you see a bad fill factor of 0.40, there can be 2 reasons. One of the carriers doesn't move, and the other one is you have too much recombination. And the way you can discriminate is by looking at the way how the photocurrent depends on the light intensity. So in one case it's 3/4, and in the other case it's 1. So that's very easy and straightforward to see. So now about recombination. Of course, in organic semiconductors, you have the so-called Langevin recombination. What means if you have an electron in the LUMO and a hole in the HOMO, that they are hopping, and that takes quite a while before they find each other. And the problem with recombination is basically that it's completely determined by the time that the electron and hole need to find each other. And for that reason, the Langevin recombination scales with the charge carrier mobilities. How can we now measure recombination in a solar cell? So if you say, suppose we have a good solar cell, and the only loss process is bimolecular recombination, then you can derive an expression for the open circuit voltage, is this one, and you see that here G is again the light intensity. Okay? So what you can do, you can say I make a plot of the VOC as a function of light intensity, and then on a log plot, the slope should be KT over Q. By the way, later on we found, we published this in 2005, that this formula was derived already 2 years before us by Eric Schiff from Cornell University, but it was in a silicon-based solar cell story that we just missed, but back then we didn't know this paper. So indeed, when you do this experiment, you see that indeed you find exactly, this is for PPV PCBM again, a slope of KT over Q at every temperature. What basically means that in this solar cell you have bimolecular recombination. That's also kind of obvious because the hole transport in PPV is trap-free, and the electron transport in PCBM is also trap-free. And if you remember what I told you about these electron traps, if they are located at 3.6, and the LUMO of PCBM is something like 3.8 or 4, then the trap is outside the band gap, so it doesn't trap. So then there is also no recombination via traps or something like that. So this is basically what you expect. We also then looked at solar cells that were a blend of 2 polymers, and the acceptor polymer here was a polymer that had the LUMO at around 3.4. So that means that there were still traps in the band gap. And what can happen then is that the hole in the donor polymer can recombine with a trapped electron, And that's the so-called trap-assisted recombination, or also it's called Shockley-Read-Hall recombination, because these are the inventors, and this is the recombination process in silicon. And I will not go into the details of the equation now, but what basically happens if you take such an all-polymer solar cell, and you measure now the VOC versus the light intensity, then you see indeed that this was the slope that we saw before, at the KT over Q, but you see that the slope gets steeper. And you can indeed explain that when you add now to the recombination, not only bimolecular, but also recombination via traps. And this, the problem was a bit that this recombination rate has a constant, and that's called a capture coefficient that we didn't know. And by looking at this slope, you can kind of use this slope as a kind of fit. You can, by this measurement, you can determine how big this coefficient is. For example, if you make it very small, that means there is almost no trap-assisted recombination. You find the old slope again, KT over Q. And when you make it too big, it becomes too steep. And for the right value, at something like 10 minus 18, you find the right slope. And with this, we could actually very nicely describe also these all-polymer solar cells. But we had to include this trap-assisted recombination, otherwise it didn't work. Now, to now look better at the process, this was done by Martijn Kuik, who is a postdoc here in Quinn's group. You can also take an MEH PPV LED and you put it under a lamp and you measure the VOC. And then you see also there that the slope is not KT over Q, but it's steeper. And again, you can use this now to determine this coefficient, which was again 10 minus 18, so exactly as we found before in the polymer solar cells. You can do this as a function of temperature. You get these coefficients, and now it turns out that they are exactly equal to Q over epsilon times the whole mobility. That's the blue line. That's in principle not so surprising. What is happening is that you have an electron that gets trapped, and before it recombines with a hole, it has to wait for the hole to reach it. So it's in principle the same as Langevin recombination, with the only difference that the electron is in a trap and is immobile, so you have to put the electron mobility to 0. And then you get basically the same expression as Langevin, except that now the electron mobility disappeared. So what is nice about this is that when Langevin you have this, then you write here the electron mobility, and for the trap assisted you have here only the hole mobility, that you know them. So if you make a hole-only device and an electron-only device, you know the mobilities and the amount of traps, and you can completely predict every recombination process, both bimolecular and trap-assisted. Another nice way to show it is when you make a solar cell or an LED, you always use two different contacts, so you get a built-in voltage over your sample, and in a solar cell you use that to sweep out the carriers. And when you now apply a small voltage, then the electric field in the device is in the wrong direction. So that means that the drift current is negative, but you still get a current because there is also a diffusion current. And now here is, for example, the IV of an OLED. So this is leakage current, so that's unwanted shorts. Then you get the diffusion current, that is kind of exponential with voltage. And then you get the space charge limited current, because when you apply a voltage that is big enough, the electric field goes in the right direction, and then the current is space charge limited, like I showed you before. And there is always something like an ideality factor in there, which nobody knows what it really is. But there are some cases where you kind of do know. And one of them was again done by Shockley and his co-workers, where they showed that when you have trap-assisted recombination, that this number is 2. And now what you do, you look at this IV, you take the derivative of this, like this, of this slope, and then it turns out that indeed is exactly 2. So what you can see directly from the diffusion current in the OLED is that in this voltage regime, trap-assisted recombination is the dominant mechanism. A nice way to make it visible is if you take a polymer that is basically a blue matrix with red and green dyes. And in this specific system, the HOMO of the dyes aligned with the HOMO of the host of the blue polymer, which means, of course, that then that the LUMO of the red dye is much lower than the LUMO of the blue polymer because they have a different color and a different band gap. So this is an electron trap, which is about 1 electron volt deep. But the nice part is, when an electron falls in, and it recombines with a hole, that it gives light. So you have trap-assisted recombination that you can see. So what you can do, you measure the white spectrum, you take a red filter and a blue filter, and then you measure the light output as a function of voltage, and you see already that the slope is different. And when you look at it more careful, then the red light has a slope of 2, which means it's trap-assisted recombination, and the blue light has a slope going to 1, which means it's bimolecular recombination. So also here, it's very easy to see what kind of recombination you have. So now about solar cells. Actually, the first thing that we did, we read the paper of Goodman and Rose, and then we knew that we had to know the mobilities of the charge carriers, otherwise we were not able to do anything. So the first thing we did, we measured the charge carrier mobility of electrons in PCBM, and that gave us that number. So you see it's quadratic, that means it's trap-free, and the mobility is 10⁻⁷, which is a bit better than the ones that you normally measure in polymers. Then we said, okay, now we take a look on the VOC versus light intensity. So I showed you before the MDMO PPV. So here we tested some other ones. But in all cases, the slope is exactly KT over Q, which means that in all these solar cells, you have only bimolecular recombination. And again, it's not so strange, because the whole transport is trap-free, and in PCBM, the electron transport is also trap-free, so there is not really a reason why there would be trap-assisted recombination. Then you can say we do something else. We now use the solar cell as an OLED. So we inject carriers, electrons and holes. Then you get this recombination at the interface, this charge transfer recombination of this charge transfer complex. And then you measure that. For P3HT, it's very hard because it doesn't really want to emit. It's not a luminescent material, so it's very low. But for the others, you can see it quite well. And you can look again at the ideality factor. And for these polymers, it's all 1. So again, it's a very simple measurement to see that in all these polymer solar cells, you have only bimolecular recombination, nothing else. Again, you can also look at the VOC as a function of light intensity. Indeed, you find for all of them the same slope, KT over Q, which you expect when you have bimolecular recombination. However, there's one exception. P3HT PCBM has a slope of something like 1.2, 1.3. So although everybody in the field is using this as a model system, it's the only solar cell that behaves different than the rest. So, of course, what is interesting is what is different. You can do another experiment. As I said, you use the LED like an OLED. And then you can also plot something like the light output divided by the current, which is the efficiency. And you see that for all solar cells, this is flat. And that is exactly what you get when you have only one recombination mechanism. But in P3HT, this efficiency rises with voltage. This basically means that there are 2 recombination mechanisms, and they each have a different voltage dependence. And the reason is this: the bimolecular or the Langevin recombination that has in the equation a coefficient and then n times p, so electron times hole density. And I showed you in the beginning in a space-charge limited device, when you increase the voltage, you increase the density. So the Langevin grows with voltage as a squared function, n times p. But Shockley-Read-Hall, that is something like the amount of traps, electron traps, is a constant multiplied by p, so that's linear in the density. So what it means is that Langevin grows faster with voltage, with charge carrier density, than trap-assisted. And that's why, so the ratio between the two is changing when you increase the voltage. So what it means basically is that in P3HT you have 2 mechanisms. That's a bit strange because when you measure the hole transport in P3HT, it looks like it is trap-free. So you don't really know what kind of traps that should be. But there is one but. When you analyze IV curves, as is done here, so here we included traps in the model, but you see that when the amount of traps gets really very small, like a number like this, we cannot see it anymore. So a trap density of 10 to the 15th you can't see, because at the moment that you apply a very small voltage, all the traps are already filled. So they don't show up. And what is special about P3HT PCBM is the following, that the Langevin recombination is reduced by about a factor of 1,000. It's still not really clear why that is, but it has consequences for the LED, because what we see is that even when the amount of traps is very small, that means that the trap-assisted recombination is also very small. But if then on top of that the normal bimolecular Langevin is also suppressed, then you even still see the small contribution from the traps. Although it is small, but because the other one is also small, it kind of shows up again. So what we believe is that that P3HT behaves different, because this one is in all the solar cells small, but in P3HT especially, this one is very small, and therefore it's in the same order of magnitude as the other one. And you can also very nicely describe it like that. Now, the last few minutes, I would like to show you something also about the excitons. This is work done by Alex Miknenko, also here in Santa Barbara, and he was also a student in Groningen. So the simple question is, I take a polymer, MEH PPV, I shine light on it, and what happens? So I measure as a function of time, I get something like this. I see some decay. And here you see it's kind of an exponential decay, and the time constant is about 300 picoseconds. Now, what does it mean? Why is it not 100 or 1,000? Where does it come from, the number? Well, what is kind of interesting, when you do this experiment for more PPV derivatives, here you see 3 of them, and what is special about them is that this one is very disordered, has a very low charge carrier mobility. This one is better ordered, has a higher mobility, and this one, because of symmetry, is even better ordered and has a even higher mobility. So we can change the mobility by about 3 orders of magnitude. And then for all these polymers, we also measured the exciton diffusion. And you see that the speed, the diffusion coefficient, that also goes up. This is not surprising, because a better ordered polymer gives better charge transport and also faster energy transport. So that's okay. What you also see when you look at the decay curves, then you see basically that the faster the excitons can move, the shorter the lifetime is. So the best polymer, the best charge transport, has a very short lifetime. And it gets even more strange when you then measure how far can an exciton walk. You can do that, for example, in a bilayer where you measure the quenching with, for example, a C60 layer and a polymer layer, and you vary the thickness of the polymer. Then you get a quenching like this. And from this decay, you can see what the exciton diffusion length is. It's for all the 3 polymers the same. So we have 3 polymers. They have 3 orders of magnitude difference in charge transport, more than an order of magnitude difference in their exciton diffusion speed, and they travel all exactly the same distance. That's kind of weird. Now you can make a small calculation. If you remember, I told you that in all these polymers, you have electron traps in the same density. So from this number, you calculate what is so about the distance between the traps. It's 12 nanometers, which means that on average an exciton has to reach 6 nanometers to travel 6 nanometers to reach a trap. So you start to get the feeling that these electron traps are also the ones that quench your excitons, that it is the same species. So what Alex did, he, together also with Martijn Kuik, here this is an electrical characterization of the Konarka polymer, and the amount of traps that was found was again the same old number as usual that you find in every polymer, this 10 to the 17 number. And then what you can do, you measure the lifetime in solution of a film, and then when you add a little bit of PCBM, and of course when you add extra quenchers, the lifetime gets shorter. And what is nice about this polymer is that all the decays are single exponential, which means that you get a very easy relation between the 1 over the lifetime and the amount of quenchers. It's a linear relation, so you can plot the 1 over the lifetime that you measure as a function of the PCBM concentration. You get a linear line, And from the slope, you can basically determine the diffusion coefficient. Now, of course, the question is, what happens now if you have also, next to the PCBM that you add yourself, if you also have some background quenchers? Then you can rewrite the equations a little bit, and then you can say, that means in the case that you have no quenchers, you have and you would know the intrinsic exciton lifetime, and for that we take the decay of a very diluted solution. You can get a relation between this lifetime in solution and the background carrier concentration. Also graphically you can see it like this. So you measure this lifetime, or 1 over this lifetime. This is the one in solution. So in order to go from here to here, you would need exactly this amount of carriers, of quenchers. And the number that comes out of these optical measurements is 6 times 10 to the 17th. And if you remember, the electrical characterization gave 5 times 10 to the 17th. So we have the very strong suspicion that all the reported exciton diffusion and lifetime data are all extrinsic, and that until now almost no intrinsic data are available in the literature. This is also important for solar cells because it means that there is a lot of room for improvement. And if we can make this length, this 6 nanometers, so which I think is an artifact, if we can make that much longer, you don't need the fancy Bullock heterojunction, but you can make a much bigger structure that maybe you can even control instead of doing it by blending and mixing and stuff like that. So let me, maybe one last slide. It's even so that in theory, when you know that all the recombination goes via traps, and that the only thing that matters is the time that an exciton reaches the trap, then in principle, when you know the diffusion coefficient, you can even calculate how many excitons reach the trap and how many recombine. And you can kind of predict the PL efficiency as a function of diffusion, and that also works quite okay. But here we have to make some assumptions about the non-radiative lifetime. But the trend is there. The slower the diffusion, the longer it takes to reach the trap. Also in the curves I showed you before. Let me go back to this one. So what happens here? If you have a fast diffusion, the exciton is generated, walks within 200 picoseconds to the trap and disappears. Here the movement is very slow, and it takes the exciton about 800 picoseconds to reach the trap before it disappears. And like I said, if the traps are not there anymore, then I think that they can run much longer distances. So some conclusions. I told you that when you have imbalanced transport, especially when one of the carriers doesn't want to move, or you have a lot of recombination, that you get a square root photocurrent with a fill factor of 0.4. That when you operate a solar cell like an OLED, that you can determine what kind of recombination mechanism that you have. And we see that in almost all solar cells except P3HT, it's only bimolecular recombination. In P3HT there is also a little bit of trap assisted. And as I said, we also observed that for the PPVs, that the amount of exciton quenchers is equal to the amount of electron traps. And that would imply that, until now we did not measure the real numbers. And with this, there are a lot of people from the University of Groningen that worked over the years on these subjects. As I said, we collaborate with the group of Quinn on the exciton diffusion. Jean-Luc helped us with the modeling, and I thank you for your attention.
So, any question from the audience? Yes.
So it's known that carrier transport on shorter time scales is time dependent, the rate of carrier transport. Do you see any evidence for time dependent exciton diffusion? Do they slow down as time progresses?
Yep, you see. Actually, that's in principle the way that until now, this is the explanation for this part here. So what you see from this plot also is that when you reduce the disorder, then what happens is you make an exciton, And it kind of, let me say it differently. If you have a lot of this order, you create an exciton. What happens is that it first relaxes to the tail states of the distribution. And during that relaxation, the exciton is still kind of hot, has still some energy, and it can move faster. And then from the moment that it reaches here this state, it starts hopping. And that's, however, when you now make a much better ordered material and this distribution is small, then it takes the exciton only a very short time to relax. And that's why we think that, for example, that the higher the diffusion coefficient, that means basically also the smaller the density, the narrower the density of states, more order, that the decay becomes single exponential. So, for example, if you looked at the numbers, this is a PPV derivative that has a diffusion coefficient of 2 × 10⁻3. You see single exponential. This is very slow, so this is this relaxation process, but it gets in time shorter when the polymer gets more ordered. But for example, this Konarka polymer, also here, if you look on the numbers, that has also a diffusion coefficient of 3 × 10⁻3, which is practically equal to the ordered PPV, and both of them have a single exponential decay. So I also believe that when you make the polymer in a nicely ordered way, that you always have mono exponential decays. And that this whole, that in the beginning it's not, because the system is still cooling down, so to speak.
Any other questions?
I must have been very clear.
So, you said that if somebody tells you the lumo of a material, you can predict the...
A polymer.
Of a polymer.
Yes.
You can predict the electron mobility. But how do you factor in order and disorder for a particular material? Are you saying that the lumo will be proportional or reflect the order and disorder and accordingly the mobility? Or?
Yeah, so it's a good question. What we see is that that we always need the same amount of trap. But when you model it, of course, you have a question, what is exactly now the width of the trap distribution? We see that it's always typically around 0.1. But now when you, for example, say it's always 0.1, then you get some different parameters that when you say when the lumo of the polymer is narrower, also the trap distribution is a little bit narrower, that you kind of scale them. And that's because you say when there is a lot of order, you could argue that also the trap distribution would be a bit smaller. We are not completely sure about that, but it gives some variation on the parameters when you do that. But in principle, the most important message is that it's always typically around 0.1, and the density is always typically in the 10 to the 17th regime. The question that people always ask is, what about small molecules? And there are almost no experimental data in the literature. And we know from experience, the people here, that it's very hard to make electron-only devices of small molecules. It's already not so easy with polymers, but small molecules is much more difficult. And there is one study done by George Malayaris in 2001 already on ALQ3, where they measured with time of flight the electron currents, and they were very dispersive. And then they purified, and it was a bit better, purified again a bit better, and so on. And in the end, they reached a nice, almost dispersive-less transport. But it was after a lot of purification. And what always surprised me was that when I started at Philips, we were making our own MDMO PPV. And so we bought the monomer and we polymerized it, let me say it like that. And then we measured, and I found this trap-limited current, 10 to the 17 traps. We measured then MEH PPV that we got from Alan, that came from here. It was exactly the same. Then in our project, at that time, Heugst company joined. They made PPVs in kilograms. Again, the same trap-limited current. And everything that we did, later on you had the group of Van der Zande in Belgium. They had a nice route to make a kind of regio-regular PPV. But whatever we measured, it was always 5 × 10 to the 17 trapped. although the polymers were made with different synthesis routes in some cases, different parts of the world, but they all behave the same. So therefore, we kind of ruled out that it was something like the remainder of a catalyst or stuff like that. We didn't believe that. And we always suspected that it had something to do with the uptake of water or oxygen in the structure, which is kind of similar. But we did not prove that. So if any one of the chemists here has a good idea what the trap could be, I'm very happy to listen to every suggestion, or especially how to get rid of it.
This is a very naive question coming from a semiconductor background, but some of those early slides where you show mobility varying by orders of magnitude with voltage made me nervous, I guess. And I wondered
With the density.
If that's the right description, or another way to put it, has anyone measured things like velocity field curves in these materials? And obviously the semiconductor then, so it's a straight line, and that, you know,
yeah, we did.
constant over some range.
Yeah, we did also transient measurements, and they confirmed kind of this picture. So what basically happens is that you in a normal semiconductor you can compare it with trap filling. That you increase the density, you fill traps, and the transport gets better all the time. In organics, it's a little bit different because these specific polymers, they are very disordered and amorphous. They don't have a band. So they are, let's say, only traps, and transport is hopping between the traps. But the concept is the same. You fill the ones that are deep, there the carriers cannot really escape from. So you can compare it in principle with trap filling. And that's why the transport gets better. But the biggest difference is that you don't have a band. And that's, I also had a semiconductor background before I worked on this.
That's why I mentioned earlier, many of they borrow from traditional semiconductor type of light organic semiconductor.
Well, what is interesting is that what you can see, what we learned over the years, that most of the traditional semiconductor models work, but they have some adaptations like a density-dependent mobility. And if you include that contains then the physics and even the morphology and all kind of stuff. But then the traditional models work quite well, actually. But you have to modify some of the parameters in the right way.
So do you ever see things like ballistic transport?
No, they are extremely slow. I mean, if you make a 1 micron film, then the transit time is a millisecond. You know, so.
The other question, Jack.
So you mentioned that P3HT is sort of weird to eventually see
Yeah.
that as recombination. Do you think that's just a function of the fact that the recombination is reduced so much, and that we probably have the same number of traps in all those other polymers?
Yes, that's very well possible. Like I said, from transport measurements, when the number is too low, you don't see them. So you know, it could be like the ultimate tail of the DOS or something like that. But yeah, P3HT is exceptional in the way that for some reason the bimolecular recombination completely is suppressed, and then it comes out. What, for example, the group of Mike McGee says is that you need this mixed phase that has a higher band gap, and that pushes the electron and holes apart, and that's the reason why also the recombination is suppressed. Could be, I don't know. But the fact is experimentally that it has been shown by many groups that the bimolecular recombination, also in other polymer solar cells, but not so strong as in P3HT. So.
Other questions? So I have one question in terms of the trap density. So in the experiment that you actually add impurity that can act as electron trap.
Yeah.
So then you will see that trap density you see will increase beyond the 10 to the 17.
Yeah, the first problem we have is that a density of 10 to the 17th, that sounds a lot in terms of charge carriers, but in analytic methods it's 0. So with the NMR you can go to 10 to the 19th when you're really very good, but that's still 2 orders of magnitude too big for us. So we miss there a complete gap. So we cannot chemically identify what the trap is because all the methods that you know, they are not sensitive enough. But what we did, for example, is to test what we did. For example, in solar cells, let me see if I can find the plot. So here, for example, what we did, we had a solar cell, which was PPV and PCBM, both trap-free. And then we throw in some TC&Q. Has a LUMO of something 4.5, so it's also for PCBM a very strong electron trap. And now you can argue that there maybe is also a bit here and so on. But what you indeed see, and that's what you expect, is that without TC&Q you have this VOC versus light intensity with exactly the slope KT over Q. At the moment that you add a little bit of TC&Q, the slope is directly 3. So this is a way how you can show that when you deliberately make traps, that indeed happens what you expect, that the slope directly goes much steeper. But adding traps, the problem is, it's the same when you add dopant to polymers. Johan knows a lot. You add a molecule in a polymer solution, they aggregate and stuff like that. It's always hard to say what you end up with. And the densities are so low that you really need that you don't know what you're doing in principle. It's very difficult.
Other questions? Okay. So if not, let's thank Paul again, and I'm sure we'll be around to answer more questions.
What about this work of Ardini where you had spin trap as a free radical and it claims that?
Yeah,
Is that real? Because other people say it really isn't real.
Well, if it would be molecular oxygen,
Yeah.
I could be real.
No,
but
he
yeah.
definitely had
Yeah.
spin.
Yeah,
He
I know,
claims
yeah.
an improvement.
Yeah.